Awesome. Thanks, Emmanuel. So I'm very excited to be here. So thanks to Cornell Database Group. So I'll be talking about some of the research we've been doing in the area of systems for human data interaction. And this is work with a lot of kind of like colleagues and friends and students in my lab. And so, the rationale for a lot of our work is that if you look at kind of like computing, right, one of the most powerful aspects of technology is that it empowers people to actually build and create for themselves, right? And interfaces are kind of the conduit for which we kind of interact with and use computing. And if you look at, any application, for example, writing, well, for millennia, since ancient Egypt, right, scribes were the main API for writing and copying manuscripts and so on. But then fast forward to now, and word processors kind of enable anyone to just open a web page and then, write your research papers, write novels, write memos, and even very nice local neighborhood announcements about kind of like, cats and raccoons and so on, right? So this is kind of, the power of building applications for people. But then what's even more powerful are tools that help you create new interfaces. And over the past decade, the tools for creating new interactive web applications and mobile applications and interfaces have evolved to the point where it's possible for a non-programmer to create and deploy these rich, interactive, scalable applications without really writing that much code at all, right? And this is thanks to a confluence of both design tools like Figma and Plasmic and Webflow that are basically like Microsoft Word, but for interface design, coupled with development tools that dramatically simplify, the work from go from design to code. And these can range from programmatic libraries like React and Svelte to these low code and no code tools like Airtable and Bubble and Retool and so on. And then the final piece, of course, is deployment, right? With, like services like Convex and Azure and all these cloud services. Storage and compute and kind of like data storage is essentially free. And this is incredible for building kind of new applications. But of course, we also know the center of gravity of the world has shifted towards data, right? And this, if we look around, this type of tooling ecosystem doesn't really exist for building human data interfaces. Like we have large scale databases, we have data science platforms like Jupyter, but the design tools, the no and low code environments, right? As well as kind of one-click deployments, all of these things don't really exist for this class of applications. And to give you a sense of what's going on, right? If we look at a traditional application interface, like a spreadsheet, for example, it's like if the interface shows 10 rows, then it really just represents 10 rows of input data in your database somewhere. But if you look at like a visualization or any data interface, that same bar chart could represent 10 records, or it could represent 1 million records, or it could represent an unbounded number of records, right? And the data that's being rendered in the interface directly aggregates over essentially an unbounded amount of data. And so that's really a core challenge, right? It's a combination of the fact that the data scale, of course, we know can affect the interface, but it's not really represented anyhow. Coupled with the fact that when you design applications, you can't just think in isolation about the systems and about the interfaces. Like the decisions that you make at both of these levels are deeply coupled together, right? There's this design dependence. So to give you a sense of these challenges, I'll start with scale. Now, if you have a very small data set, we kind of know what to do. You can just spin up any browser, build kind of a JavaScript application, run kind of like JS, SQL.js or DuckDB in the browser, and you're pretty much done. But then if the data set grows in size, then you might have to then, revert over to kind of like a server based kind of like processes, maybe use a laptop or a machine. If you have even larger data, then you might have to go across a network to communicate with a remote server somewhere, which might be running a separate database. And then if it's even larger data sets, then you might have to go to the cloud, right? And all of this, of course, introduces latency at every single system boundary. Right? It introduces network bottlenecks, it introduces cloud API calls, and the fact that now you're running a distributed system. And of course, the user at the very top sees the same application. Like they don't really care that you have this problem, right? They just expect the same, interactivity and the same design. And so now we typically add caches everywhere across the system in order to hide these latencies. And we might want to query these caches or process data in these caches. Then you start looking like databases sitting around everywhere, right? And of course, we have like incredible libraries to solve any individual problem. But optimizing and combining across them together is highly non-trivial, because if we squint and step back, this is essentially the memory hierarchy all over again, right? Rather than CPU, caches, and memory and disk, we have browsers, laptops, servers, databases, and cloud, right? And we know that programming against this is a fundamental challenge in computer science. And we're asking designers to manually program and optimize against this kind of new type of memory hierarchy, right? And this kind of signals a lack of good abstractions. So that's the issue of scale. And it's then, compounded with this issue of design dependence. So if we consider a very, very simple example, right? I just want to create this simple interface to analyze legislative votes from different chambers of Congress. And so on the right side, we're going to show like a trivial client-server architecture and different types of pre-computational optimizations, right? As simple as it gets. Now, if you wanted to, for example, add 2 buttons where the user can pick the decade, right, that they want to analyze, then we kind of know how to optimize this, right? We can pre-compute, the chart for each of the decades. And when the user clicks on the 2000 button, then you can just send the pre-computed data over. Very, very easy. We also know that if we change this to a range slider, then we have to basically throw that optimization out the window, right? And we essentially, we can't just pre-compute a quadratic number of, minimum and maximum date ranges. So we're going to have to use a different data structure, right? And you might even be a little bit smarter and say, let's push that to the browser, push the data cube to the browser, and we're going to do all the execution there, right? All of these are system optimization decisions that you have to make. But what if you then add a radio button, right, to select the chamber of Congress that you're interested in? Well, then you have to throw the previous optimization away, right? And so what we can see is that any minor change in the interface design directly affects the optimizations that are needed. Even in this very, very trivial case, we're just looking at very simple types of optimizations and a very simple application design. And so this is kind of like the challenge, right? Like designers have to think not just about design, but about the system and system design implications as well. And so the life as a designer shouldn't be so tough, right? Like the trend in most application development is going to easier and easier and easier. But because of this combination of scale and design dependence, it's become harder than ever before to build these applications. And we see this all the time where, you'll build like a very custom like data management system for a very custom type of interaction, for a very custom type of application and use case, right? We see this everywhere. And so this has motivated us to pursue 3 classes of problems. It's under this umbrella project of the data visualization management system. At the foundation, what we're looking for are system primitives that can make it easier to express and to build data interfaces. And on top of that, we're developing systems that more easily design interfaces at scale. And we are also looking for declarative representations that can express kind of like a rich set of applications. And then at the very top, if we can make it very easy to build and design data applications and interfaces, then what more can they do than simply displaying data or clicking on widgets, right? Like what other capabilities don't yet exist that should exist? And so this is kind of like the suite of projects that we've been working on over the past half decade in my lab. And so what I want to do is talk about like one slice of them. And I'm not really going to focus on the technical details, but really like the problem formulation and how we're thinking about these. And then if you're interested, of course, we have papers online. So the first one, I'll start at the bottom. And we're going to talk about this system called smoke and smoke duck, which reframes interaction as lineage operations. Right? And this is work originated with Fotis Salidas, and then it's kind of continued with Hanin and Charlie. So given a data flow, such as a join here, right, we might want to join on the color on ID, followed by aggregating on the color or the ID attribute, right? And then what fine-grained lineage is the record level dependencies between operator inputs and outputs. Okay, so for example, if we look at the output O1, well, that depends on the join results J1 and J2, the orange ones in the middle, which depends on A1 and B1 in the input tables. Right? And this, of course, forms a graph that can tell you the inputs that contributed to any output records and vice versa. And this is, of course, very useful, for debugging, for privacy, for analyzing distributed protocols, and kernel review maintenance, many, many applications. It's already very useful. However, fundamentally, the way we actually materialize and capture this lineage graph is actually quite expensive, right? And traditional techniques incur a 10 to 1,000x or more query slowdowns. And the main idea is because a very, very fast read optimized query has now turned into this very large write operation because you have to generate all of these pointers somehow. right? And so the typical approach, right, is that you can augment kind of your query, right, and augment, what you submit to the database, so that in addition to the data that you're actually trying to compute, you're also going to annotate, right, into intermediate as well as output results with these lineage IDs. So these are just record IDs that tell you, well, for a given intermediate or output record, well, what input records are dependent on, right? So for example, here you might annotate kind of like the intermediate join result. And then finally, after the aggregation, you're going to also annotate the result with the lineage information. Now you can see here that, of course, it blows out both the size of the intermediates and the outputs. And also the aggregation result should have only had 2 records, but instead we have 3, right? Because we're trying to stick to the relational model. So there's many other ways that you can capture lineage, but in general, it's very, very expensive. Now, the reason that we actually care about capturing performance and lineage performance is because it's also a very natural way of expressing interactions. Because if you think about, the screen, well, anything that you point to the screen on is either layout information or it represents data. And that data is, generated and stored somewhere, right? And the pixel is just some representation as the output of some computation. So for example, if I select kind of points in a scatter plot, what you're really pointing to is the backward lineage, right? The input data that it actually they visually represent. And if you can imagine, if the base table has been rendered in a different way, for example, like a bar chart, then typically we might actually want to do some refresh or forward lineage operation in order to update it in response to what I selected in the scatter plot, right? And all of this we should be able to express declaratively. For example, all we're doing is that we're just joining what we've rendered with kind of the user's selection box. And then we're basically doing a backward lineage plus a refresh. And so the nice thing is that by using lineage as a first class kind of citizen in terms of expressing applications, we can really think of the visualization and the interactions as a combination of SQL, right, to render the initial visualizations, plus lineage and more SQL to express the interactions. And of course, it's not limited to just visualization, right? Because data, of course, is rendered and manipulated in many, many forms. For example, you might actually want to reference the lineage that you selected in the scatter plot and then use it as input in another query, right, in a Jupyter notebook. Or maybe you want to fit a model to that data instead. And so lineage really is simply the correspondence between what you see on the screen and data, right? That's all it is. And so it goes far beyond just visualization. And the problem is that it's nice to express this stuff, but no existing systems can actually use lineage to kind of power these interactive applications, right? On the other hand, we know that fast visualizations do exist. And so there's kind of a gap between what lineage systems currently provide and what we should be able to be capable of. And so the Smoke and Smoke Duck projects are intended to fill this gap. And so over the past several years, we've been building several different query engines to efficiently materialize lineage and be able to drive these interactive applications. And the main idea is when you execute a query or a data flow, you want to materialize these lineage indexes that tell you the relationships between inputs and outputs on a per operator basis. So that when you then point to an output result, you can just traverse along these indices and get the lineage, right? And then you can, of course, do pre-computation, all these other classic database tricks. And so in this context, Smoke was our first work. In VLDB 18, we kind of showed that this is actually possible by building a custom query compilation engine that's row-oriented. And we showed that, you can actually get this to interactive performance. And then our current work right now, Smoke Duck, is to show that, hey, like actually in Columnar open source engines, right, and vectorized engine designs, you can actually get this almost for free as well. And to show that this has wide applicability. And so I want to just give you an intuition of how this works. Right. And so I'll use filter as an example and show you what Smoke does in our VLDB 18 work, and then how Smoke Duck kind of actually does it. So in here, right, if we have like filter operation, and we have 3 input records to the filter, right, and we want to check, okay, which records have a money greater than 20. And so lineage is going to be this kind of red array, and it's just simply an integer array. And so as we execute filter and we look at the first row, then we see that, okay, it passes the filter. And so what we simply do is in the corresponding offset in the lineage array, we're going to keep track of the record ID, right? So that's 1. And then we look at the second record in the input, and it doesn't pass the filter. So we go to the third one. It passes the filter. So in the corresponding offset in the lineage array, we then store its record ID 3. And that's really all it is. right? So lineage is simply an integer array, right? Either one-dimensional, two-dimensional, depending on the operator. And it's very, very cheap to create and populate. And you can integrate this into the query execution itself. So you're not doing extra work. You can piggyback off the existing work. And so in our VLDB work, we ran it on TPC-H with scale factors between 1 and higher. And so what I want to just show is some of the relative numbers, right? And so these numbers are relative to hand-compiled queries. So we basically took the equivalent queries, we hand-compiled them and wrote them in C++, and that's what we're comparing against, right? Prior approaches, in comparison to Postgres, incurred 200 to 80,000% overhead, right? Depending on the TPC query. And here, what we're going to see is that Smoke incurs between 5 to 22% overhead, right? And the reason is because we're not doing extra work. We're really just kind of piggybacking off the work that's already been done. And so that was very exciting for us. But then, of course, no one's going to use Smoke because it's like a custom engine. It's like a PhD kind of level code. And really, it's not really general. And so the question is like, what about an actual like vectorized engine, right? Because columnar engines is what people actually use for analytics. They're typically vectorized. They have all these optimizations. And so we've been looking, and so let's look at what columnar engines actually do. In something like filter, we're not going to actually read all of the records, right? We're just going to read one column that corresponds to the predicate. And it outputs a selection vector where each kind of offset corresponds to a Boolean value saying, did that record pass the filter? This is a selection vector. But if we compare it to the lineage data that Smoke generates, we can see that they're actually equivalent, right? The selection vector that filter generates in a columnar engine is just a dense representation of the same thing. And so it turns out that late materialization engines actually already compute lineage as a side effect of query execution. And this is fundamentally the case. And this is kind of like what we've been exploring over the past year. And so if we look at kind of like the numbers here, now what I've done is I've copied over the numbers for Smoke, but the Smoke duck numbers, right, which is where we extend the DuckDB vectorized engine, is relative to DuckDB. So the relative numbers are not apples to apples. But it's just to give you kind of a ballpark figure. So when we run the same kind of benchmark using Smoke Duck and DuckDB, we see that the overhead is between 1.8 to 5% overhead, right? And the reason is because in many of the operators, you literally are doing no work other than pinning an existing data structure in memory, right? And so this is very nice. And then the other kind of like positive thing that we identified is that it doesn't take that much lines of code in order to actually do the instrumentation. It's about 4 to 20 lines of code. Many of them is simply just like pinning something into memory, right? And at that point, then you can decide whether or not you want to flush it to disk or do something else. And so this is very exciting for us. And so rather than kind of like showing you numbers, it might be good to just show kind of a demo of this in action. All right, so we're going to just show this cross-filter application with 5 million records. And what cross-filter basically does is you have a bunch of kind of like different views over different attributes. And when you select a range in one of the views, then you want to filter for the subset and then use it to re-aggregate and re-render the other views. Now, traditionally, what you would do, you would build a data cube, and it might take kind of seconds to minutes to build this thing. And what we're going to show is that with Smoke Duck, you can express all of this using backward and forward lineage operations. And then you don't have to do any pre-computation, right? Any like overhead work other than capturing lineage itself. So this is kind of like observable notebook where we're going to first show you kind of like what happens when you use the just pure DuckDB. Right. So the idea here is that we've rendered kind of like three of these charts. And then every time I basically select data in one of these charts, then we're going to just go back and rerun these queries, right, with appropriate filters. And then at the very top right here, you can see that it takes about 700 milliseconds in order to answer the most recent kind of request or recent interaction. And this is because, of course, like it's just doing a lot more work. And then so we can also look at Smoke Duck. And so I'm refreshing the screen. And so what's happening here is as we generate these visualizations, it's also materializing the lineage at the same time, right? And then when you actually start performing interactions, it's using the lineage information as essentially an index to do selective view refresh, right? And the nice thing is here is like if we want to add like a third chart, we can easily do that. It takes basically no overhead in order to actually render, and then you can do basically the same kind of interactions, right? Okay, yeah, my laptop is dying because Zoom is running. But you can see that the query latencies are on the order of individual milliseconds. So this is actually quite nice. And the other powerful thing is that you can also access lineage programmatically. For example, here, what we're going to do is we can actually create a view where we just simply want to count the size of the lineage that's been selected from the first view, right? So I'm running a query where I'm using lineage as basically a data source instead. And so when you do this, then you can also select data here, and you're going to see that the corresponding, like query result is going to be updated. And so this is kind of like very powerful because underneath the covers, of course, there's a lot of complexity, but none of that complexity really is necessary for expressing and optimizing the application. And so that's kind of like the idea of smoke duck, right? We've been studying essentially the extent that these ideas can apply to late materialization engines and how to cleanly integrate lineage management into kind of like the data management system. So that we can actually get like 4 decades of like amazing lineage kind of applications and theory and research into like, people's, hands, right? In something like very popular like DuckDB. And it seems also that many arrow-based systems like Data Fusion and Arquero and so on are also amenable to these kind of ideas as well. So that's just one example, right, of how a core concept in data management can be motivated and improved by thinking about its application to user-facing interfaces, right? And of course, the same can be said for many other ideas, ranging from networking to client-side caching, federated execution, and so on. So very exciting. But now what I want to do is shift to the top and discuss some of the novel interactions and capabilities that data management perspectives can provide to interfaces. And so I'll talk about, this very briefly. And so the question here is, what should interfaces be capable of, right? And even if we just restrict ourselves to interactive visualizations, it can be very interesting. And it helps then to first look at, well, what are the types of interactions that are common in toolboxes today, right? And then use that to then identify, well, what other interactions might be interesting. So a very common one, of course, is interactions, right, with an interface to create new charts, creation and organization of new visual representations. And the common one, of course, is Tableau's shells, right? You drag attributes from your data onto the X and Y axes and so on, and then you can render a chart. What's happening under the covers is very simple. This is a projection, right? You're projecting date to the X attribute. You're projecting some function over cost to the Y attribute, and then you're rendering it, right, using SVG objects or using WebGL and so on. Another class is to manipulate data within a chart, right? So for example, when you zoom, what are you doing? Well, you're basically filtering in and zooming into a smaller date range, right? Or you're zooming out to a larger date range. When you do something like transformations, you're really just saying, well, instead of computing average, I want to compute max or something else, right? So you're changing kind of like the aggregation function. And then with something like filtering, well, you're basically adding a predicate. And if you look at something like coordination across interactions across multiple charts or multiple views, then it's very similar, right? Cross-filtering, for example, is the canonical kind of interaction paradigm. And this is where you select data in one chart, for example, this bar, and you want to see the corresponding kind of like subset of data in another chart, right? And this is adding a filter. And so if we kind of like step back and look to a first approximation, all of these interactions boil down to manipulating the select and where clauses of a SQL query. Right? But the thing is, of course, we know that SQL goes way beyond this small class of queries, and of course, beyond these types of query transforms, right? And so now we can start saying, well, what properties of queries do people actually want to manipulate, and how can we then turn those into novel interaction designs? And so one of our recent work kind of like studies this by saying, well, what about kind of interactions where you compose and compare multiple charts, right, or multiple data across multiple charts? For example, here, what if I want to compare SFO and Oakland charts and see kind of like their comparison? What does that mean, and how do you express that? And for example, think about what a line chart really is, right? What it is it's like a specific design that facilitate comparisons between prices over different time values, right? And it does so by aligning these values using a shared y-axis, right? And so it doesn't do anything else, right? It's optimized for this particular query, this particular type of analysis. And when we design kind of applications like Google Finance, then we basically are designing for some set of preordained comparisons that we hope to facilitate, right? And for example, here we have the line chart, but of course we have also stock prices here, stock prices of other companies, other stock price data, and so on. And so the question is, all of this is data that a user might want to compare with each other, but you cannot right now, right? The only interaction paradigm for comparing this stuff is to stare at one number, remember it, and then look over at another part of the screen and try to do a mental calculation. And so can you externalize this type of interaction? And so this is the idea of what we call view composition algebra. So this is work that we're presenting this year at Viz. And let me just show you kind of a very simple demo of what that means. So this is kind of like a demo that kind of looks like the Google Finance visualization. And the idea is that anything that is computable, computed over data, is something that you should be able to compare with each other. For example, maybe you're interested in knowing, well, how does like Google's current stock price compare with Amazon's over time? Well, can we do that? By unioning them together, right? Or maybe I want to compare, right, Google's stock price with Amazon's stock price and look at the difference. Then what does it take for us to be able to point to any data, right, that's compatible on the screen and be able to compare them together, right? And so this is the kind of class of interaction that really doesn't exist today, but should exist. And the nice thing is this is a very uniquely data management problem, right? One question is simply, what compositions are safe, right? This is a data integration problem. For example, we somehow know intuitively that this line chart, right, that computes hours and prices is compatible and composable with average price, with price, but not really with volume. So it is but in general, right, any visual representation of data can be computed over arbitrary input data through arbitrary transformations. And so what is compatible with what else? So this is a very interesting question. Another one is, what are the semantics to begin with, right? When you compose two arbitrary pieces of data in the visual domain, then what should the results be? And so what our paper does is define kind of like these semantics and safe compositions for Tableau-like visualizations. But of course, Tableau-like visualizations is a very, very narrow class. And so how do we go beyond that to arbitrary kind of visual representations? So that's that's using data management to motivate interaction design. But there's of course another class of comparisons that you guys are intimately familiar with as well, which is comparing data with mental models, right? So these charts are from the Chi 17 paper, same stats, different graphs, right? They all show exactly the same summary statistics up to precision of 2. But they're clearly very different. And so visualization is exactly powerful because it shows you what statistics might not able to ahead of time. And so can interfaces now help users compare with their expectations? And so this line of work started with Scorpion, right, which is query explanations. And the idea there is the simplest way for a user to really tell the interface what's expected is just draw it and show it. And so, for example, here, maybe we're generating like sensor data, and we're grouping by hour and computing a standard deviation of temperatures. Then the user might ask, well, what's going on in a particular region? And you'd like some system to be able to tell you, hey, you know what, it's the sensors with low voltage, or some descriptor over your data that's kind of causing this to happen, potentially causing this to happen. And so you might then say, oh, let me ignore bad sensors, let me do something about it, and so on. And of course, this work, there's great follow-up work by Peter Bayless, Sudeepa, Alexandra, and many, many others in the area. And so this is another class of interactions that simply doesn't really exist, right? It's not something that's out of any toolbox. And then, of course, there's many other types of variations that can also be useful. And so one recent work that we've been working on is taking the same idea, but thinking about it for training data debugging. And the idea here is, for the classic problem is I want to visualize kind of like sensor data over time, right? But what if I, in the middle of my query, I actually want to make a prediction, right? And so what I'm actually doing is I'm filtering on a prediction, or I'm grouping by prediction, or I'm using a prediction in some way, and then I'm visualizing the results, right? In this case, if the user, sees that, oh, like hours 3 and 4 had this precipitous drop, and that seems surprising, then existing explanation approaches simply help you identify errors in the readings table, essentially your test data set, right? But what we also know is that these errors can occur from data that was used to train your model M, right? And that the model errors could be the source of kind of like the errors that the user is seeing on the screen. And so really the question is, can we use kind of like, this information from the user to identify errors in the training data instead? And so we've been kind of working on this, right? And the real question is like, how do you estimate kind of like how training records contribute, right, and affected query output complaints? And overall, all of these are variations of kind of like the same theme, right? Which is the user asks the questions about data on the screen, and the system should provide some explanation. And ultimately, these explanations are a function of the lineage, right? The user points to data. This is what they care about. And they care about, of course, how that data was computed, what data was computed on, and so on. And so it's ultimately a function of lineage. And so this is another reason why we work on lineage systems and fast lineage capture, is because we believe that it can enable a lot of these different applications and these different types of interactions. So I want to switch gear and talk about one last class of work, and this is precision interfaces. So far, we've focused on building interfaces and expanding their functionalities, right? But interface design ultimately is dictated by the analysis task, right? And the analysis task initially is very ad hoc. You don't know what it is. And we want to, of course, design an interface once we've settled on the queries that are actually going to be needed, or the class of queries that are needed for a given analysis. But if you think about interface creation tools, right, they kind of work in reverse. They first say, we're going to be really good for this class of analyses, and you can build interfaces in this class, right? And so if we kind of like look at the tools available for creating new data interfaces, then we can categorize them by expressiveness on the x-axis, right? And then how easy it is to then use these tools to create new interfaces on the y-axis. And we can see basically on the upper left, right, it's, there's these systems like Metabase and Tableau and Superset. They're very, very easy to use, but they're essentially restricted to parameterized queries and data cubes, right? Things that you can express there. And then if you want anything more, then you're really in the arbitrary domain, right? Where you're basically going to use these tools like VegaLite, D3, Python, and so on to make your programming life a little bit easier. But effectively, you're going to have to write a lot of code and pay a lot of money in order to kind of go beyond, these simple classes of analysis. And so the big question is that, we can build more libraries to make programming easier. But can we just automatically design interfaces for any analysis task, right? And what does that mean? And how do you even think about this as a problem? And so precision interfaces is like one approach that we've been kind of exploring over the past several years. And it kind of follows this philosophy, which is an interface, we can model it as a set of visualizations that render query results, right? You do some analysis, you run a program, you get some data, and you visualize it. As well as interactions that let users essentially change these programs in some way, right? They can be drop downs, they can be drags, they can be whatever, but basically any mode that you can interact with a computer, right? You can use it to interact and then change the program. And you can imagine now going through and listing just all the queries that you could possibly generate by all possible combinations of interactions. And you can call this set of queries its expressiveness. So then now, what is an interface? Well, an interface is a compact representation of a set of queries that it can express, right? And hopefully, right, we hope that when we design an interface, that class of queries includes ones that are relevant for the given user, right? And so, in this context, then what our work is saying is, let's have some representation of a sample of queries in this analysis kind of like class, and then try to derive the latent interface. And you can imagine there's many different ways of doing it. But ultimately, the core challenge boils down to, how do you define a model for mapping from queries, right, query strings, to interactive interfaces, meaning the layout, the visualizations, the interactions. And what I'll do is kind of like walk through the 4 main steps of how we're currently thinking about it and approaching this, and then show you a demo. So the first step is to think about queries as their parse trees or some tree representation. Now, the reason we care about focusing on parse trees is because then we can be independent of any individual database's query plan representation, right? And then let's focus just on the highlighted parts. So these queries, query 1 and query 2, are the same, except where A equals 1 and B equals 10. Right. And the interface here, if you just do this, is very simple, right? We just run some visrec tool on each query result and just render them as charts. Easy. But of course, maybe you want to do a little bit more, right? And so what we introduce is this notion of free variables or choice nodes or parameters, whatever you want to call it, to encode subtree variations. For instance, one variation can simply be, I can choose between these 2 queries, right? In which case, then what that means is this any operator can choose between one of its k children. And then we can now say, well, this variation is exactly what an interaction is meant to kind of fill, right, to map to. And so now we can render, of course, this entire tree as one visualization, right, the output of this tree. But then we can map kind of buttons or any kind of interaction to this choice that I can make. And so when the user kind of clicks on, say, b equals 10, then effectively we would then choose the second subtree, right, and then render the query results for that. And of course, then we can use different types of interactions as well. Rather than kind of a drop down or buttons, we can use radio button and so on. And so, of course, we need a cost model to rank different valid interactions based on whatever kind of measures, right? For example, usability, screen size, et cetera, et cetera. And then the final thing is to notice that the middle tree is really just the result of merging the initial pair of trees, right? And this is just a tree transformation called merge. And this allows us to generate interfaces that are structurally different. For example, right, the interface on the left has 2 charts. The interface on the middle has 1 chart and then 1 set of interactions. But we could also imagine refactoring this middle tree by pulling the shared kind of equals up, in which case then we can independently select the attribute as well as the constant, right? In which case then we would then map each of these different choice nodes to different interactions. And we now have a structurally different interface that can also generalize beyond the 2 input queries that we started with, right? In practice, of course, we have many, many different transformation rules and the different types of choice nodes in this toy example. But this is kind of like the intuition. And you can wrap this up in machine learning, right? So you basically, to put this together, we transform queries into a tree representation, right? And then we basically map individual trees to visualizations, right? Query results to visualizations. We map these choice nodes to interactions. And then we map the tree structures themselves to layouts. And then we can then cost the resulting interface and decide, hey, is it good enough? Or should we then perform some transformations, right? And internally, we're going to use some kind of stochastic search process, right? We use Monte Carlo tree search, but you can use whatever kind of like else search algorithm. And so this is essentially what's going on underneath the covers. And so I wanted to show you a demo of this kind of like working in practice. And so I have kind of like this very, very simple kind of interface for this demo where I'm looking at kind of like the cars data set, right? So I can submit this query, it renders the results, and then, present interfaces, chugs for a while and then says, here's a chart, right? At this point, this is no different than any visualization recommendation system. And you could even replace PI with this thing, right? But now, what if I say something like, oh, I actually want to change and look at a different range, right, of horsepower. So then the system will chug along for a while, and it'll say, oh, you know what? Why don't you, instead of kind of like modifying the queries manually, use the slider instead. Now you can say something else, like, for example, I want to actually write a subquery. Now, right now, I'll just write a very simple one, but you could imagine a very, very complicated one. So I'll say something like, well, the origin is equal to USA, right? So this is effectively a filter, but I'm just going to show that you're structurally changing the query, right, beyond just adding predicates. In this case, the system is pretty simple. It just says you can like visualize kind of like the cars, the full data set, or you can look at just USA. Pretty straightforward. But if you then change this to say, well, what about Japan as well? Then you can basically submit this to the system, and the system will realize, oh, okay, we actually have some structural transformations in place, and we want to modify just the subquery, right? So you can pick between like the full data set cars, we can pick between modifications of the subquery. And now, finally, what if you say something like, I actually also want to look at horsepower and the average miles per gallon from the data set, right? And I want to just group by horsepower. And so you kind of like run this query, and then what the system will do is chug along for a couple seconds, and then it should hopefully generate interactive visualization. So here it recognizes that, oh, in addition to rendering this new kind of like query, what I can actually do is add interactions so that you can actually see which horsepower average miles per hour that you can select, and then use that to interactively kind of filter the other chart, right? So this is kind of like the interaction dynamics. Like as you kind of like perform your analysis, or you just give this one shot to the system, then it can incrementally generate these interfaces, right? Now, admittedly, it doesn't look great, right? It could look better, it could be styled better, and so on. But functionally, it's actually quite good. And so the reason why we think this is very exciting is because we think of this tree representation, right? It's kind of like this intermediate representation that represents both the analysis as well as the interface, right? And what I've talked about so far is how you can use SQL queries to generate this representation. But you can imagine, this representation is over ASTs. So you can do this for pandas as well, right? And where do you get these queries from? Well, it can be from SQL notebooks. It can be from natural language, right? And so on. And so it's a very nice kind of representation that we think, could be very promising for as kind of a target. And so, in our demos, in our paper, we kind of show different applications. And so one thing that we kind of see in industry today is that there's more and more of these like SQL-oriented analysis notebooks, right? There's kind of like Jupyter Notebook, of course, there's Hex, there's Count, and these other kind of notebooks that are oriented around data processing in SQL. And so what we basically show in our demo is that we can instrument something like Jupyter to basically integrate this kind of functionality into it. And so what you can do is basically select queries that you feel like are representative of the kind of analysis you want to perform. For example, here we're analyzing kind of SDSS data, and you can select 2 queries. You can click Generate Interface, and the system will generate an interactive interface that you can use alongside your programming. Right? So that's one potential application. Another one could be kind of natural language interfaces. Right? So in this context, we've kind of like built a demo where you can ask this question, like, what do COVID cases and deaths look like in California and New York? And then the system will generate an interactive application for you, right? And then you can use that interactive application, right? And the nice thing with kind of like having a full control over the representation of the analysis and the interface is now we can do other things, like, for example, generate tutorials, right? How do I use this application, right? And what are the sequence of steps that I should take in order to perform an analysis, right? Then you can then automatically generate tutorials and so on. So now I talked about these 3 projects, right? And these are kind of like 3 within this like larger umbrella system. And so I just wanted to connect it with kind of our vision overall. So the interfaces that we generate using precision interfaces are, of course, in this internal declarative representation, right? And the idea with this system called physical visualization design is we want to take this representation and then recommend a backend system, right? The set of physical optimizations, and essentially generate middleware that's customized for this application representation. So you can think of it very similar to physical database design, but the data structures are all created and stored outside the database, right? And you have to account for the client and the server and communication and so on. And so this is nice because now we can design an interface, point to Snowflake, and then fill in the architecture in between. And of course, this can hopefully be then executed using the system primitives that we've been developing, right? And then, of course, we can then, if we have full control over the interfaces, then we can embed these novel interactions and functionality that we've been talking about, right, as we design and optimize and deploy. And so we really think of kind of precision interfaces as this way of bootstrapping the use of kind of a lot of these other projects that we kind of have in our lab. So with this, hopefully it's like a useful overview or a helpful overview of kind of the work that we're doing in our lab, right? Many disciplines in computer science are merging together, and data and how it's used is completely in flux, right? And we have really the opportunity to kind of define the goals ourselves. And so if there's one thing that you kind of like take from this talk is that at the intersection of different disciplines, in this case, data management and visual representations, right, there's rich types of research that can be informed in both directions, right? And both in terms of novel capabilities, in terms of interface design, in terms of systems work. So we've tried to study some of them, right? And hopefully that was very interesting. All right, so that's it for me. I'm happy to take any questions. And I see I have like 10, 15 minutes.